All right, so questions over homework. Obviously, I can't go through like 4 different examples or else it'll be the end of the class and we won't cover anything. So let's see if there are any requests over any particular problems. We'll pick like the most requested one. 37? Which one was that one? The rocket. Rocket. What chapter are we in? That's chapter 2, section 7. 37? All right. A television camera is positioned 4,000 feet from the base of a rocket launching pad. All right. So I have this. Y'all ready? Everyone? Okay. I have a camera that's positioned 4,000 feet from the base of a launching pad. So here's going to be my point. I'm going to call it just C for camera, okay? And then over here I have a point which I will call L for the launching pad. I know that the distance between these two is 4,000 feet, and that appears to not be changing throughout the entire problem, right? The base of the launching pad doesn't change where it is. The camera doesn't change its position. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Also, the mechanism for focusing on the camera has to take into account the increasing distance from the camera to the rising rocket. Let's assume that the rocket rises vertically and its speed is 600 feet per second when it has risen 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? If the television camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing? So this is actually 2 problems in one. All right? They're 2 separate things they want to know. Does everyone understand that? First, they want to know, for part A, how fast the distance between the camera and the rocket is changing. And then the other one is how fast the angle is changing. 2 completely separate issues. So what I'm going to do is I'm going to draw this rocket. It's being fired vertically. So it's going to follow a path that's straight up like this. And I guess I'll put a point there. That'll be my rocket. I'll label it R. For part A, I'm interested in knowing the rate at which the distance between the rocket and the camera are changing. So I'm going to draw a line connecting the rocket to the camera. Preferably as straight as I can get. There we go. That's a pretty good line. What am I given? What do I want? When do I want it? Okay, the rate at which the rocket is changing. It's going up at 600 feet per second. So that point, the black point there, is going up at that rate. So I need to look at that as a side that is changing by a certain amount. So we can call that side of the triangle anything we want. And I think we used Y before because it was like parallel to the Y-axis. So I can call this Y. That's the distance from L to R, right? And this is a right triangle. I'm going to put the little right triangle symbol in there. I'm given that the Y is changing at a rate of 600 feet per second. So I'm given the dy dt is 600 feet per second. Everyone agree? What do I want to know? The rate at which, for part A, I want to know the rate at which the distance between C and R is changing. Yes? Correct, because it's moving straight up. So Y is getting bigger instead of getting smaller. So if it was the rocket coming down or something, then it would be, you could use negative. Okay, so I want to know the rate at which the distance between the camera and the rocket is changing. I have not labeled that side of the triangle. I heard h. I'm fine with h for hypotenuse. So I want to know what dh dt is. When exactly do I want that? When do I want that? Okay, when what's 3,000 feet? It says, let's assume the rocket rises vertically at a speed of 600 feet per second when it has risen 3,000 feet. When y is 3,000, right? When the rocket is exactly 3,000. So when y is equal to 3,000 feet. Now let me try and draw my picture at the instant in time. I know that the 4,000, this leg of the triangle doesn't change. At the specific instant in time, I know that my y value, right, is 3,000. And if I know two sides of a right triangle, then I'm going to know the value of the third side, right? So if you do Pythagorean, a squared plus b squared is c squared, you should get h is what? Should be 5,000. Because it's the square root of 4,000 squared plus 3,000 squared. Right, square those, add them, take the square root, you should get 5,000 there. Everyone okay with that? All right, so all we need now is an equation that relates y to h. I look into my general picture. How can I relate h and y together? If I actually know this side is always 4,000, I have a right triangle there, don't I? I have the relationship is that this squared, 4,000 squared plus the y squared must equal the h squared. That's the equation I can use. So my equation will be 4,000 squared plus y squared must equal h squared. And that's the one I'm going to differentiate, right? Differentiate that with respect to time, right? To time, to t. Now, I could have squared 4,000, but I know I'm going to take derivative of it, and that's a constant, right? So derivative of that constant is 0. Derivative of y squared is 2y dy dt equals derivative of h squared 2h dh dt. And now this should have everything I need, right? Do I know y at the instant in time? 3,000. Do I know dy dt? Yes, 600. Do I know h at the instant in time? Yes, we had solved that triangle, hadn't we? Do I know dh dt? No, but that's what I want, right? So everything looks good here. So I'm just going to plug things in. I could kill the 2's off, couldn't I? Okay. Y was 3,000. Let's try and get our units here, because someone was asking me about the units. I've left the units off the whole time, haven't I? And just said at the very end, look at your units and see what's happening. Let's try and do it with the units and see if we can get it to work out. This 3,000 feet. What's dy dt? 600 feet per second. So is it okay if I put over 1 second? Isn't that the same thing as 600 feet per second? Okay, equals h. What's h measured in? Feet also, right? So h was 5,000 feet times dh dt is what we're looking for, right? Now let me just take care of the units first. Does everyone agree I could divide both sides by feet and just those feet would cancel? Yes? But this feet wouldn't because I had 2 feet over here, right? I had feet times feet. So those feet cancel. And the only units left are what? Feet per second. And look at the dh dt was supposed to be our answer. I said h is measured. That's a length, right? Should have been feet. And time should have been seconds. And we're going to have feet per second left still. So you can try and keep track of it throughout the problem, or you can just go back and look at the differential and get the units. That's your choice. So I'm going to multiply 3,000 times 600, and then divide by 5,000. What is that? Anyone do it? 360? That's it? Feet per second. Anyone else get the same thing? Or is that what the back of the book says? Okay. So you multiply 3,000 by 600, divide through the 5,000 on both sides, and you're done. Does anyone have any additional questions on that problem? Like in your drawings, you mean? Were you like? Mm-hmm. You put the H as 3,000? Yeah. Yeah, see, and that's all going to depend on your drawing. So that's the challenge, I guess, in the problem is getting your drawing to go with what's happening. And, you know, there's different ways people can draw it, but we should all get to the same result. I would recommend that if you want some additional help on this, that you come by and sit down, because I need to kind of see your logic, like how you're thinking through the problem. I can't just, you know, I can show you how I'm doing it, but when it comes to you sitting and doing it, the only way I can help you is to be like, okay, now how are you interpreting that? Draw it. What does that mean to you? And then seeing if that drawing is making sense. And if it's not, then I can kind of help you say, okay, we'll look at it this way. You drew this exact same picture right here, like this? You did Y here and H here? What did you put for this? And you put for here? E? Okay. So then, did you realize that your H was changing by 600? Did you do like dH dt with 600? Okay, yeah. We probably should just sit and go through one of these, because your differential, your d whatever dt, will always be connected to your picture. It always has to be. It has to be something on your picture that is related to this variable, and there has to be something on your picture that's related to that variable. That way you can come up with the equation somehow. If you start putting in additional variables that don't appear here, like dr dt, then if r is not up there, you're never going to get that dr dt out of the equation. Okay. Practice more problems and okay. Gosh. Yeah. We'll move out of this section. We could spend the whole other 3 weeks in this section if we wanted to. I think we've got the gist of it, and we'll move on. The what? Oh yeah, sorry. I forgot about the B side. I apologize. I forgot. Okay, so that's the first. That's just the distance between them. Now let's look at the other question, which was finding the angle, the rate at which the angle was changing. So we still have the same exact picture. We've got the station on the ground. We've got the rocket launch pad. We know that that's 4,000. That's not going to change. The rocket's being fired straight up. That's not going to change. The angle is actually going to come off this triangle. But the angle now is what we're interested in, not the length of that side, right? We're interested in theta as opposed to how fast that side's growing. Still going to label this side y. I'm given still the rate at which y is changing with respect to time. That's still 600. I want this time what, though? The rate at which, so the rate is the d, okay? The d whatever is the rate. So d means rate. Rate of what? Theta. with respect to time. I want that. When do I want it? Same thing, right? When that y coordinate is 3,000. So my drawing of exactly the moment in time has this thing over here fixed at 3,000, which means, of course, this side is 4,000, and that theta is the angle. I can actually find theta now, can't I? Because I know that there's a trig function that relates the opposite and adjacent sides of a triangle to that angle. It's tangent, right? So I'll be able to find the theta for the exact moment in time. Do you want to go find it now? We can, or we can wait. We're going to need it eventually. Find it? I know right now that tangent theta is 3,000 over 4,000, which is 3/4, right? And now to solve for theta, the only way to get theta out of the tangent is to come in on both sides with inverse tan, or arctan. So I take inverse tan on both sides. And that means on the left side, the inverse tan, the tan wipe each other out. On the right side, I do arctan of 3/4. So on your calculator, you do that. And make sure that you know what mode you're in, because your answer is either going to come back to you in radians or in degrees, depending on your mode. So somebody do that and tell me what the answer is in whatever mode they're in. 36.87 degrees. Okay, anyone do it in radians? No? Okay, we'll use degrees. All right, so I know that that's what theta is at the exact moment in time. Now, let's get the equation. How are you going to relate that y to that theta? How do you relate this y to this theta? Same exact equation, right? Tangent. Tangent relates this side over this side. I know this side. It's 4,000. So it's probably going to be useful for me to do that. I know tangent theta equals y over 4,000. I'm going to get rid of the fraction on the right by multiplying both sides by 4,000. I just did that because I didn't want to get all messed up with, like, am I going to need quotient rule? Or, just get the 4,000 on the other side. Now it's just a constant in front of tangent. Now the derivative. Any questions? Derivative of a constant times a function. The constant stays there. Derivative of tangent theta is secant squared theta. Drum roll. D theta dt. So what we did is we said, what's the derivative of tangent of my hand? It is secant squared of my hand. Then you go inside, what's derivative of my hand? What's derivative of theta? D theta dt. So chain rule there. We talked about it last time. What happens if that theta, d theta dt doesn't happen, right? Well, you're never going to be able to solve for it, right? It's not in your equation, so you can't solve for it. So you should know that you're going down the wrong road if the d theta dt, which is what you want, doesn't appear in your derivative. It's not there. How are you going to tell me what it is? What about the right side? Derivative of y? dy dt. Do you know what theta is? Yes. D theta dt is what we want. Dy dt, do you know what that is? Yes, 600. So we have everything. So it's a matter of plugging it in. Now remember, on the secant theta, you can just use your calculator for this, because you know now that theta is, what, 36.87? But you would need to remember what secant is. So I'm going to write this out. This is 4,000 times secant is the same as 1 over cosine, And then theta is 36.87, 87 or 78? 87? 87. Okay, that's what secant is, right? Yes? But then we have to do what? Square that. I'm just going to do it like this, just to really stress. Like, that's the way you do it on your calculator. You do like 1 divided by this, figure out what that is, then square that answer, then times 4,000, right? Now, next to that, you have d theta dt. And on the other side, it was just 600, wasn't it? I'll get my calculator out. Make sure I'm in radian or degree mode. All right, so in here, I'm going to bring this up here. I have 4,000. Inside that bracket, 1 over cosine, I got 1.25. And then I'm going to square that. D theta dt equals 600. So square that answer, and then multiply times 4,000. I get 6250.02 d theta dt equals 600. Is that all right? Square the 1.25, multiply times 4,000, and then now take 600 and divide it by that. Get 0.096. D theta dt is 0.096. What are my units? Radians per second. And why is it radians? Well, I told you, right? Radians per second. I told you that whenever you do problems like this, your answer is always going to be in radians. If it's a measurement of the rate of change of theta, even though you were in degree when you went and did that, cosine of 36.87, that's just a number, okay? Doesn't matter if you had plugged in the radian or the degree measurement of the angle. This is just a number. And so your end result will always be in radians per second. Is this the answer in the back? Yes? Okay. Question? You used cosine? If you used cosine, then you did 4,000 over... Okay, but what did you use for the... Did you use tangent for the equation you differentiated? You didn't use tangent at all. That should have presented a problem. Because you used what as your equation? Cosine of what? Okay. So x over c. And then you got negative sine theta d theta dt equals, did you quotient rule? Oh my goodness. Dx dt times c. Yeah, it'll be the right answer as long as you did everything else right. Hold on. All over c squared, okay. Now so your picture looked like this then. You had x, you had c. Did you call this side anything over here? Y, okay, and you called that theta. So d theta dt is what you wanted in the problem. You don't have dy dt anywhere in this, do you? How did you figure out what dx dt was? Like part A? That's right. That's 0, okay. And then you use the answer from part A here? That'll work. That would work. But I would argue the other one was yeah. You know, I've always told students when it comes to math, you know, you're trying to get usually from point A to point B, and there's an infinite number of paths that lead you to that answer, right? And what, you know, after many years of experience, I'm getting pretty good at getting the shortest path to that answer. As a student, you might go on a path like you did, but as long as you get to the result, you get to the result. You probably gained a lot more by, you know, you had a lot more differentiation to get right there than I did, because you had to get that quotient rule correct. You had to realize that dx dt was 0. Yeah. Yeah, you could have replaced this right here. You could have said 4,000 over c. Okay? And then you wouldn't have needed a quotient. But anyway, it works that way. But now that you've seen the other one, the reason why I stuck with tangent was exactly because I knew this side was fixed, right? And I knew that this side, I would get a dy dt out when I differentiated, and I knew what that was. Yes? Oh, yeah, you could do that too. You're saying, in other words, to find secant squared, you rewrote that. Oh, yeah, that's pretty clever too. What's being suggested here, which worked, is just using the identity that this is 1 plus tan squared theta, right? And then tangent is 3/4, right? Tangent theta was 3/4. So this is the same as 3/4 squared, which is 9/16, and you added 1 plus 9/16. 25/16. Yeah. Yeah. It all worked out the same. Yeah. I think that's probably the thing that I enjoyed most about math when I was learning it, is that as long as you don't break any rules, as long as, you know, again, going back to this path thing, you know, as long as you don't break a rule, your path may be different than someone else's, but you should all arrive at the same result. The problem that I see in like college algebra and even in classes like this is as soon as you break a rule, you're not necessarily even on the same piece of paper anymore, right? Like you're somewhere else now. And the only way to actually get to point B is to accidentally break back, you know, unbreak a rule, or, you know, do something to fix your mistake earlier, and all of a sudden, wow, you fall into the answer. But that's luck, really, if that happens. But everything else, as long as you follow a rule, you should be okay. Now, you might get yourself stuck in like this infinite loop, you know, where you're sitting here like that, and you're not breaking any rules, but you're not going anywhere, you know. That might happen also. But no one can tell you you're wrong at that point. You're just crazy at that point, right? What's Albert Einstein's quote? It's like, the definition of insanity is doing the same thing, expecting different results. So it's like, you know, you're just kind of doing the same thing over and over here. And anyway, I hope I made a point, but very good. I think that's great. I mean, use something completely different, use something completely different. They both got you the same place. You wouldn't get taken off for that, you know. And the way that I do it is just the way that I have done it since I started doing these. It's just, that's the way. And you know, when I went to school, my goal was never like, I'm going to go teach calculus. Like, one day I'm going to teach calculus. It's just, as a student of math, as a graduate student, we had to tutor people, we had to help. So it seemed like when I was explaining it to people, people were understanding it, and I just always tried to explain it the way it made sense to me. And sometimes people will come in with a different approach, and I'll be like, oh yeah, I never thought about it that way. Yeah, that works great. You know, it's just whatever makes sense to you. So another way that you could have done this, you went and used the identity. Secant squared is one. I could have just found out what secant was off this thing anyway. Like, We knew that this side was 5,000, didn't we? Okay, secant theta, right, is the reciprocal of cosine. Cosine of this angle is adjacent over hypotenuse, so secant is hypotenuse over adjacent. That's 5/4. So I could just said 5/4 squared. See what I'm saying? There's so many different ways of doing it. The reason why I went in and did it the way that I did it there was just, I don't know, that's just the path I chose for this one. All right, very good. I've always said that for Cal 1, I think the major results, like the major concepts that I like students to get out of it, are related rates, curve sketching, and optimization problems. They're the hardest of what we do in this class. Related rates are very challenging because the word problems, translating it, drawing the pictures, connecting your variables, kind of bringing everything together into one problem. And it's also real life stuff. I mean, for this, it doesn't make sense, right? Like, do you really need to know the camera stuff? But there are more advanced problems that later on use the same methods to do the problem. Anything that's moving, if you can connect one to the other, you can find out what's happening at instantaneous, at instance in time. Like, it could be a piston moving, it could be, you know, the recoil of what do you call those howitzer, you know, anything that moves in times going by, which is pretty much everything. You can find out instance of impact, what? Artillery, whatever, anything. You know, war has always motivated us, right? Right? We love killing everyone, right? We love it. So whenever we want to kill people, right, we need bigger weapons, we need better weapons, you know, right? I'm not saying me personally, I'm saying mankind, right? I mean, at some point we're just lobbing rocks at each other, and then we figure out, you know what? That lob is a parabola. And I know that parabolas have x-intercepts, so I can actually predict where that lob's going to fall. I don't have to just throw it anymore. I can actually figure out where I want it. And so the math behind it all really motivated, I mean, well, the need to hurt and kill and say, this is mine, and your God sucks, my God's better, and all that stuff is made us, you know, the math has progressed that. I don't know. You can disagree. I'm giving my opinion. But you cannot deny that advances in science are usually motivated by war. This is not a political science class. This is not a sociology course. So let's just go to chapter 3 before I get myself in trouble up here. All right. Related rates behind us. We'll see those on the next test. Chapter 3. Anybody familiar with George Carlin? He's my favorite comedian. Inverse functions. Oh, wait, chapter 3. Chapter 3 is called Inverse Functions. Now, I have these lecture notes that you hopefully have been following, and you know, this is chapter 3, Inverse Functions. I'm just going to breeze through this because the first two sections, 3.1 and 3.2, are all reviews from college algebra. I'm not going to get into big-time detail. But there are some major concepts we need to remember, and it's been a long time, so let's just review them real quick. Exponential functions. Very different than power functions. An exponential function is a function where you write it, f of x is a to the x. The a is called the base, the x is the exponent. So the a is actually a number, and the variable appears up in the exponent. That's different than, you know, the difference between x squared and 2 to the x. X squared is a quadratic, it's a polynomial. The variable is in the base, the number is up top. This is an exponential function. The variable is in the exponent, that's why we call them exponential functions, and then the base is always a fixed number. When you look at exponential functions, they all have to look something like this. Okay, we talk about exponential growth, right? Takes off, goes up very fast. The other direction, it's going to go and converge to some number. So for any function, a to the x, as long as that a down there is bigger than 0 and not equal to 1, it's going to be exponential. Now, if that a right there is bigger than 1, so if it's like 2 to the x, 3 to the x, e to the x, what's e? E is a number, right? It's about 2.7 something, so that's bigger than 1. Anything that's bigger than 1 down here is your base. This is what the graph looks like. As you go out to infinity, to the right, it goes up to infinity. As you go to the left infinity, this thing gets smaller and smaller, approaches the x-axis, so it goes to 0. That's what these two pieces of information say, right? X goes to positive infinity, function goes to positive infinity. X goes to negative infinity, function goes to 0. Now, if you change the a, and the a here is now less than 1, but bigger than 0, so like 1/2 or 1/4 or like 0.2, anything that's less than 1, what happens is the graph flips over. And so your graph goes to the left to negative infinity, it goes up forever. To the right, it actually goes down to 0. So the red picture is called exponential growth. The blue picture is called exponential decay. What you need to be aware of is how they behave. If I say, what does 3 to the x do as you go out to the right? What does it do? 3 to the x. What is it going to do as I go to the right? It's going to go up to infinity. What does 1/2 to the x do as I go out to the right? It's going to go down to 0, right? And so you have to be familiar with that. That's what this is saying. Also, we had all those properties of exponents. You know, if you have something to a power times the same thing to a different power, you add the powers. If you have division, you subtract the powers. You all remember those? If you have something to a power, you multiply the powers. If you have two things being multiplied to a power, you can apply the power to each one. Can you do that if that's a plus in there? A plus B. No, you can't do that. But if it's A times B, you can do it. All right, so that's just exponential stuff that you should recall. For the log stuff, inverse functions, the idea of an inverse function is that you have a function that does something, and then the inverse function comes in and undoes it. So like if you have a function that, let's say you have a function, you call it f of x equals 2x. That function takes something in and doubles it, right? So if it takes in the number 3, it spits out 6. The inverse function has to take 6 back to 3. So the inverse function takes the 6 back to 3. How could I do that? Cut it in half. So I could take half of that value, x. So the x now is the 6, and it goes through and comes back as a 3. So the inverse function, that's the way we write the inverse. Do you all remember ever seeing that little symbol? Would be 1/2 x. So if f is 2x, the inverse of that is 1/2 x. If 3 goes into f, comes out 6. If 6 now goes through the inverse, it comes back 3. That was a general idea behind the inverse. What this note is saying is that, I don't remember. Did I go down too much? Well, right here. No, this is what I wanted. It's a review. But the log functions, okay? The log functions are just the inverses of the exponential functions. So for every exponential function, there is a function that undoes it, and it is the log function. So if you have an exponential function, 2 to the x, you plug in an x, it's going to spit out a number, right? If you want to undo that, you have to come in with the log, and the log will take it back to where it came from. And not just any log, it has to be the log base 2 function. So whatever the base is here determines the base of the log. So this is what all log functions look like. They all have to have a base. That base must be a positive number, and that base can't be 1, just like with exponentials. And the reason why is because it's the inverse. So whatever applies to the exponential has to also apply for the log. So that has to be bigger than 0 and not 1. if the a is bigger than 1, this is what it looks like. So let's talk about this property, or the properties of this graph. If I go out to infinity, a log function should do what? Go to infinity. Don't forget that. Now, it's slow growth, right? It's not exponential. It's not like taking off. But it is slow, but it is going, right? The further out I go, the bigger it gets. So it does go to infinity as I go to the right. Now, as I go to the left, the graph actually runs into a major problem. You cannot go to the left of the y-axis because log functions are not defined on negative numbers. So you can't like figure out what the log of negative 2 is. It's impossible. So whatever you plug into the log must be positive. In fact, you can't even plug in 0. If you try and plug in 0, it's undefined. So what happens is as you try and approach 0, notice this limit has a little plus on the top of it. That means as I'm approaching 0 from the left side, my graph is diving down to negative infinity, right? That's what this means. With me? Now, that's if the base of the log is bigger than 1. What if it's smaller than 1? Well, then your graph does that. This time, as I go out to infinity, the graph is going where? Down forever. So negative infinity, right? And then same thing, as I try and approach 0, run into a problem, but now my asymptote is going to go up instead of down. So it dives up like that, or takes off up like that. You think you can handle the ideas here with the graphs? You really have 4 situations, don't you? You have a to the x, with that number being bigger than 1 or less than 1. You have log base a of x, with the a being bigger than 1 or less than 1. In all 4 cases, you need to know how they behave. Then you had all these properties of logs. I'm going to use these today, so let's make sure you understand them. There was a point in college algebra where you were probably asked to condense or expand logarithmic expressions, and you used all these properties. It said if you have a log and you have 2 things being multiplied inside the log, you could split it into 2 logs. Do you all remember that or not? Or you could go the other way around. If you had 2 logs, you could put them together into a single log. That's this property. If you have division inside of a log, you could take it and turn it into 2 logs with subtraction. And this was a huge property. We're going to use this today. If you have log and you have x to a power, that power can come out. That was big time. That's going to really help us today. So with logs, powers drop out. And then there was with all of these exponential and log functions, since the base could be any number that was positive, right? It could be 2, it could be pi, it could be 4, it could be anything, right? 1/2. There was a very special number, a very special base, that if we used it, right, we called it the natural exponential function, and that's the base e. So e is this very special number that when we use it as our base, we call the exponential function natural exponential function. And when we use log base e for the log, which would be the inverse of this, right? We called it the natural log. Do you all remember that? So e to the x and natural log of x are inverse functions. Whatever one does, the other one undoes it. Now, a little bit of background, because I think this is worth talking about. When you were learning about logs, and they gave you like y equals log base a of x, they said that's a function. They said the a here could be any positive number, right, but just not 1. And so you could have, like, as examples, the log base 2 function. You could have log base 1/3. You could have log base pi would work, right? You could have log base 10. But wait a minute. Whenever it was log base 10, they said you don't have to write the 10. Do you remember that? They said instead you just write what? Log, right? X. And then they said if you have log base e, you don't have to write the base. You just write ln x. So like for all the other logs, you're supposed to put the base there, right? These are the only 2 special logs that you can use this special notation for, right? You know, remember seeing that at all? Let me tell you why. I think it's worth talking about, because I think that that's one of the most confusing things for students, is that they lose complete sight of the fact that there is a base on this log and it's 10, and there's a base on this log and it's e. In my opinion, we should just always write the base all the time. That way there's no confusion, there's no loss of knowledge or anything there. Here's why they didn't. Because I should say log base 10 function and the natural log are used all the time. Anyone ever taken chemistry courses or like physics and pH and all that? You're using base 10 scales, and so log base 10 is used so much. The natural log is used all the time. That back in the day when people were like writing dissertations, like 400-page papers on some study, and they would have all these equations in their papers. We're talking about like research scientists and stuff. They would have to be justifying their work. So they would have like log base 10 all throughout this paper. Back in the day when they had typewriters. And has anyone ever tried to subscript on a typewriter? Everyone know what a typewriter is? Yes? You know, so when you subscript, you're typing, and then all of a sudden you have to do like this half rotation of the drum, and then back, and then. Now imagine you have like that appear into your dissertation like 1,000 times. You're sitting there, you know, it sucks. So what they did is they said, look, if you ever need log base 10, just do log x, and then you can type without stopping. If you ever need natural log of x, just do ln x, and you can just keep typing. And nowadays, we still couldn't switch back to this, right? Because have you ever subscripted in Word or anything? You just copy paste? Well, but yeah, you could do that now. Yeah. But I'm just saying it's not going to flow real nice, right? Log x will flow. Natural log x will flow. You just keep typing. Nothing stops you down, nothing slows you down. So that's why we do it. It's just for ease and convenience. Now, these functions are so special, and I'm going to tell you why. This e to the x is so special to us. I'll have to explain geometrically why it is. But what happened was, for the longest time, scientists were trying to find a function that behaved a certain way. They're like, I wonder if there is a function that has this property, and this property. And they went out and they tried to find the function that behaved that way, because if they could, then they were going to be able to solve a lot of really tough problems. Well, they found it, and it's e to the x. Now, I'll explain to you why it's so special, but you're just going to have to wait, all right, when we get to the next section, 3.3. So we have the natural exponential function, we have the natural log function, and here are the properties that you need to know for these two functions. If you take e to the x, that means you're plugging x something, right, into e, and then you come in, you do the natural log of it. Since the natural log is the inverse, isn't that just going to spit out what you started with? That's kind of like that loop I showed. The 3 went in, it became the 6, you came in with the inverse and went back to 3. Well, if you plug x into e and then come in and do its inverse and do natural log, then it's going to spit the x right back out. So that's why that property works. The natural log of e to the x is x. It works the other way around. If you take x and plug it into natural log, figure out what that is, and then plug that into e undoes it and spits the x back out. I just see like this x like falling back out. Do y'all see that too? Y'all don't see like an x going in and all this crap happening to it and then it just comes all back out? That's what I'm visualizing. All right. E to the 0. Anything to the 0 is 1 except 0 to the 0. We're going to have to handle that today. But in general, any number to the 0 is 1 as long as the number down here is not 0. And e is not 0, so we're not worried. The natural log of 1 is 0. Why? Why is the natural log of 1 0? Well, where does e take 0? I'm going to draw a picture up here. If I plug in 0 and I send it through the e to the x function, where does it send it? 1. Okay, what's the inverse of e? Natural log. So where should natural log take 1? Back to 0. So that's why natural log of 1 is 0. Right? Y'all see that little loop happening? The natural log of e is 1. Why is that true? It's this property right here. If I replace x with 1, isn't that natural log e to the 1? Yes? And so it's just taking that 1, the 1 goes into e, natural log undoes it, spits the 1 back out. These are all things these three right here, 1, 2, 3, those three you should not need a calculator for, you should not need a book for, you should not need your notes for. Those should be like automatic. Maybe they weren't today before you walked in, but I'm saying from here on out, those three should not need reference. Okay, we also had what was called the change of base formula. This is this was something in college algebra that, at least when I teach college algebra, I explain this by trying to explain why your calculator only usually has 2 keys on it. Your calculator usually only has the log key and the natural log key, right? There's no special key if you want to do log base 4. So you're like, well, wait, I paid $150 for this calculator. Why doesn't it have a log base 4 key? Well, because anytime you have a log, it doesn't matter what the base is, and you're trying to find like log base 4 of 10, let's say, you can always use this formula. And that formula requires that you only have a natural log key on your calculator. So you can convert any log over to this using this and solve any log. So it's a very important formula. And now we get to derivatives, right? If all of these are functions, then we can talk about their derivatives, can't we? Yes? You got to do something. Go do jumping jacks, do something. Wake up. Right? I mean, so far we know the derivatives of like all these polynomials, like x squared, derivative of that's 2x, derivative of sine function, cosine, right? Derivative of tangent secant squared. We've got a pretty good bag of functions that we can take derivatives of. But I have conveniently avoided exponential and log functions, haven't I? I mean, like everything we've done up to this point, they have not appeared. Now it's time to address them. How do we figure out what their derivatives are? So as a geometric explanation as to what we're looking for, if we had this, let's say this is f of x is a to the x. In this case, a would have to be what for this picture to match that? Bigger than 1, right? A would have to be bigger than 1 for this to be the case. When I'm saying, what's the derivative of f? Okay, and that's what we're here to talk about right now. When I'm saying what's a derivative, it should represent geometrically the slope of the tangent line, shouldn't it? So like I should be able to go out to some point here, say x, go up, the slope of that tangent line is f prime of x, isn't it? Which would? Would the derivative look like the original function? That's a great question, would it? Almost. You want to try and sketch it below? What does the derivative of this look like? Well, is the derivative ever 0? Like, is the slope of tangent line ever 0? No. So, but would you agree that right here it's like maybe some positive number? So like the derivative here would be positive, and then over here, if I did the derivative, the slope of the tangent line would be positive still, but a little steeper. So it'd be like over here maybe. So that's a little steeper. How about back here? Is it still positive? Yes, but it's not as steep, so it'd be like this. And then as I go this way, what's happening to my tangent? It's getting flatter and flatter and getting closer to 0. So you were seeing that connection? Absolutely, that's great. It does look like it, doesn't it? This is for people who really got their heads around, if I give you a graph, can you graph its derivative? If you are comfortable with that, then you can see that if that's f up there, this is its derivative down here. And they are very much related. They're very similar to each other. In fact, I wonder if they're exactly the same. What if the derivative of that is exactly this? Well, it turns out there's only one function that exists that actually happens. Guess what it is? E. E to the x is the only function that when you take its derivative, you actually get the exact same function. If it's 2 to the x, the derivative of that isn't exactly 2 to the x. It is, but it's off a little bit. So as you're going to see right now, I start with the derivative of log. I'm going to move to the notes. Since we're talking about it now, it makes more sense. If f of x is a to the x, and you want its derivative, right? So the derivative of that, so the derivative of a to the x, is, look, itself, a to the x, times natural log of a. Now, a in the problem will always be a number, won't it? A is the base. And the natural log of a number should just be a number. So what I want everyone to realize is that this right here, natural log of a, is a number. This is the original function, a to the x. So your answer is just your original function, but somehow scaled. It's either stretched out or shrunk. That's the whole thing. I mean, so it looks very much the same, except a little bit of stretching has gone on. So I'm going to now say the derivative of f of x equals a to the x. So what is the derivative of an exponential function? It is itself times the natural log of a. That's one of the main results today. So as an example of this, if I tell you that y equals 3 to the x, and I tell you to find y prime, you're going to say it's what? 3 to the x times natural log 3. And you could get on your calculator if you want to, and you could tell me what natural log of 3 is. You're going to get some number, right? Some decimal or something. And so it's just your original function times some number, so it stretches it out or shrinks it. So they should look pretty close to each other. Just keep in mind that is a number, right? Okay, let me ask you one more thing. Same exact one. Find y triple prime. The third derivative. So what's the derivative? First derivative we just said was 3 to the x. Be careful with your verbiage on that. It's 3 to the x. If you say 3x means 3 times x. I know you know what you meant, but just work on that. So 3 to the x, right? Y prime would be 3 to the x, natural log 3. Now I take the derivative again. What's the natural log of 3? It's just a constant, right? So it's going to come along for the ride. So I'm going to say y double prime. Let's bring that constant. I'm going to bring it right now. There's the constant that was sitting in the back, right? There it is. I'm just going to bring it with me. Now, what's the derivative of 3 to the x? 3 to the x, natural log 3 again, right? So you have another natural log of 3 popped out. That's really just natural log 3, that whole thing, the whole thing squared, times 3 to the x. Now, I come again. The natural log of 3 squared is a constant. Bring it down. That's what I'm getting at. Yes, you do not do product rule because the natural log of 3 is a number. It's not a function. Is that okay? Whoever said that? Who said that? Did you say that? I'm just hearing voices, so yes. If we have a number in front of a function, like let's say we had 4 times sine x, then you take the derivative, the 4 just comes along, and then you say derivative of sine is cosine. This natural log of 3 is just a number. That's a function. So when we go to the next derivative, we bring it along, and then we take the derivative of that, which repeats itself. And then we're going to have 2 of them. Now, so I put these here's my constant coming here. What's the derivative of 3 to the x? Again, 3 to the x, natural log 3. This is going to turn out to be natural log 3 cubed times 3 to the x. That's our third derivative. Questions? Could you do what? Yeah, I think you see the pattern, right? In fact, there would be, look at this pattern. If I asked you to take the nth derivative of this, it would be natural log 3 to the n times 3 to the x, wouldn't it? That would be like a big, like a formula for the derivative, right? If I want the 100th derivative, it's just natural log 3 to the 100th. We wouldn't actually have to go figure them all out. That's just because pattern recognition, we would see that. All right, let's try another example. What if y is equal to e to the x? That's like 3 to the x, isn't it? I mean, it's just an exponential function. Find y prime. So it's e to the x times natural log of e, isn't it? But isn't that 1? Isn't natural log of e 1? Yes. So that means it's just e to the x. That's exactly why. Well, it's a little bit more challenging to convince you that that's true, because I have to convince you that this formula works. But there's other ways I can show you that the derivative of e to the x is this. It's way beyond this class. Something you could address in Cal 2. So this is a major result. So much so I'm going to put it in a box. If y equals e to the x, y prime is itself. I really want you to understand what this means in terms of a picture. Sorry? Well, yes. Yep. This is the only one that does that. But look at this. Let's say I just go out to 2. I need someone with a calculator. Somebody take 2 and plug it into the e. So e squared. Someone do e squared on their calculator. 7.39. So the height of this function is 7.39. Right? That's a point on this graph. You plug in 2, you get 7.39. Now, if I go and I ask you, what's the slope of the tangent line here? What's that slope equal to? 7.39. Why? Because the slope is exactly equal to the height of the function there. Because it's its own derivative. It's the only function that behaves that way. Every point you go to, if you go to the point you say, what's the slope? All you have to know is how high you are. There is no other function that does that, which makes it so unique. Well, there is one other, but it's called the non-trivial example, and that's the function y equals 0. Y equals 0 is a flat line. Right? What's the derivative of 0? 0. So if you go to the slope of the tangent line at every point, it's 0, right? Which is the same as the function. But this is, do you see why we call this a trivial example? Like, how useful is the 0 function? You plug something into it, it spits out 0. So that function is never really going to apply to anything in the real world. The exponential function, on the other hand, applies to a lot of things. All right. So let's try to get our heads around a slight adaptation to what we've looked at, the chain rule. We've seen chain rule, right? So let's say I have something like this. Y equals a to the u. Then the derivative of this, well, a to the u is an exponential function, isn't it? It's like a to the x. So you would say the derivative of that is itself, natural log of a. But then chain rule says you have to go up there and look at what was up there inside and take the derivative of that. For us, that would be u prime, the derivative of u, whatever it might be. This is a more general definition of the derivative of an exponential function because, you know, if you have like 3 to the x, then this x prime is going to be 1. But if you have something like the next example, y equals e to the sine x, what you have is composition. You have an exponential function, but up in the exponent is not just x, it's actually another function. So you have a function plugged into a function, that means chain rule. So what I start with is first of all saying, what's the derivative of e to my hand? E to my hand, natural log of e, but natural log of e is 1. Or you could just say that, hey, I already know that the derivative of e to anything is exactly itself. Nothing else needs to be written. Then times chain rule, what's derivative, what's up there? Cosine x. And notice that that cosine x is down here. It's not up there. It's down here. It's this whole thing multiplied times this. See how that worked? Let's do another example. How about y is equal to x squared times 4 to the x squared? What do you see? Product rule, right? Y'all see the product rule right here? So the derivative of a product will be the derivative of the first one. I'm going to go slow on this first one. Times the second one. Plus the derivative of the second one times the first one. So that's our product rule. What is the derivative of x squared? 2x. So we have 2x times 4 to the x squared plus, what's the derivative of 4 to the x squared? So the base is not e, right? The base is 4. Anytime the base is an e, it's always going to spit out that little natural log a thing. Okay, so the derivative of 4 to the x squared is itself times natural log, in this case, 4 times 2x. Where did that 2x come from? The derivative of what was up here, because that was chain rule. And then what do we still have out there? X squared. Do y'all see that? Derivative of 4 to the x squared is itself natural log 4. Now derivative of x squared is 2x. What, this whole thing right here? It would need to be in parentheses if I had a plus anywhere in here. But because I don't have a plus, I can leave it without parentheses. Another one. That looks weird, right? X to the 10th, 10 to the x. Find y prime. What do you get? 10x to the 9th times 10 to the x plus 10 to the x natural log 10 times x to the 10th. So we have four things here. There. Those are our four things, right? If we broke this thing up and called this one F and this one G, this was F prime, this was G, this was G prime, this was F. I'm just trying to show you just different ways of looking at all this. I don't want to lock you into a certain box where you always look at everything the same. I guess the moral of this problem is you need to know the difference between taking the derivative of x to the 10th and 10 to the x. You won't believe how many people on the quiz that you're going to take at some point. On a quiz, I'll give them this problem. I'll ask them for the derivative, and they will put, guess what I get? X 4 to the x minus 1. Don't laugh. No, you can laugh. I can't laugh. Because then if someone does it, it's like, oh, they were laughing, and he's laughing at me, that was rude. You can laugh. I mean, do you see what a fundamental error that is? You do not apply the power rule, right? They tried doing 4 comes out, then subtract 1. You cannot apply a power rule to an exponential function. You can apply a power rule to a power function, which is like, what, x to the 4th? Yes, then you can go 4x cubed. But if it's that, you cannot. We clear on the difference? So, yeah, no go. Yes, that's good. So what would that derivative be? 4 to the x, natural log 4. All right. All right, I think we've kind of exhausted the derivative of exponentials. Let's now move to logs. How about I give you the derivative of logs in its most general form with the chain rule already. So that way we have the most general form of it. Chain rule applied to the derivative of a log. Okay, if you have y equals log base a of u. Now that u could be an x, but it's just we're going to act like it's something else. Then the derivative of this will be 1 over u times natural log a, so the natural log a is on the bottom, times the derivative of u. Sometimes people will prefer to write it this way. So people will say, oh, the derivative of log base a of u is first just to put the derivative of u and then divide it by the u natural log a. So you really only need to find two things in order to find the derivative of a log. You have to find the derivative of what's inside and divide it by what's inside and then multiply it by the natural log of a. That's what this formula says. So as an example, if y is equal to log base 2 of x, what's y prime? I'm going to do it to the side so I can get more examples here. So for us, the u is really what here? X, right? So I like to do it the first way I wrote. I say that the derivative of natural log of, or log of anything is 1 over whatever that anything was. So for us, it was x, right? Times the natural log of, in this case, 2, then times the derivative of what was in here. What's the derivative of x? With respect to x, we're going to say 1. Okay, so we are assuming we've kind of moved back now. We're assuming that we're taking derivative with respect to x right now. So it's going to be 1. So your answer is just 1 over x natural log 2. What about this one? Y is equal to log x squared plus x plus 1. What is our u? What is our u here? X squared plus x plus 1, right? So my derivative should be 1 over that u, x squared plus x plus 1. But then times what? Natural log of, if it's not written there, it's a 10, right? It's a 10. So you have to remember that. You have to understand that. So if I put natural log of 10 here, since that's a number, I must put parentheses around that x squared plus x plus 1, because that natural log of 10 would have to distribute through to each of those. So it would have to be in parentheses. Am I done? No. Times the derivative of what was inside the log, which is 2x plus 1. Do I need that in parentheses? Yes, because it's 2 terms. And so if you prefer the other form, you put the 2x plus 1 on top. You put the x squared plus x plus 1 on the bottom with the natural log 10. You all following this? What if y is equal to the natural log of x? So what's u for us here? X, so it's 1 over x, natural log of, careful, e, right? Because if it's not there, well, if it's just a log, L-O-G, it's 10. If it's ln, that's e. ln comes from, I believe it's French. They do everything kind of backwards, right? Natural log, instead of that, it's log, like logarithmic and natural or something like that. So it's L then N. I don't know. I may have made that up a long time ago. I'm not sure. That's the way I remember it, though. That's what the ln is. I have a bunch of pre-calc students that tell me, like, yeah, I'm using my IN button on my calculator. I'm like, it's not IN. It's ln. Really, I don't make up a lot of stuff in here, okay? I might have made that up and then convinced myself to believe it after all these years. Okay, natural log of what? E, but what's natural log of E? That's 1. Now, I'm supposed to take derivative now of what's inside, which is 1. So what does that really all just turn out to be? 1 over x. And that is one that you should remember, for sure. There's actually 2 that are big time today. What's the derivative of e to the x? Itself, e to the x. So what's the derivative of e to the x? E to the x. What's the derivative of natural log of x? 1 over x. What's the derivative of natural log of x? 1 over x. Now, if it's something other than x, we got to do some work, right? Let's try another one of these natural logs, but this time what's inside won't be so simple. It's 220, my goodness. What if y is equal to Natural log, let's do negative natural log of cosine x. Negative natural log of cosine x. What is that negative in the front going to do? Is it a constant? Can we just bring it along with us? Okay. So the derivative will be the negative. I'll just even put 1. Now, what's the derivative of natural log of something? 1 over that something, right? 1 over itself. 1 over the cosine x. And then because it's natural log, I do times natural log of e, don't I? And that will always be a 1. So you never have to put it there. Just like when we were doing derivative of e to the x, we didn't have to put that natural log of e there because it's always a 1. So this will just be 1 over cosine x, and then times the derivative of what's inside here, negative sine x. But wait a minute, we have a negative 1, we have a negative sign, that's positive sine, isn't it? Over cosine. What's sine over cosine? Tangent x. Huh, interesting. In Calculus 2, who are my Cal 2 fans? Yes? Who's going to Cal 2? Okay. In Cal 2, the whole beginning of Cal 2 is doing what are called antiderivatives. So derivatives, a derivative is like this. Okay, you go, take the derivative, and it becomes tangent x, right? Right here, this is called differentiation. You start with the function, you take its derivative, it's called differentiation. Calculus 2 is backwards. So you start over there, you come back the other direction, this is called integration. And what makes it so challenging, is that if I have a product over here, right? If we have a product and we have to do derivative, we know that the product rule is going to make that look pretty ugly over here. Now imagine trying to go backwards from that. So it's like trying to undo product rule and quotient rule and chain rule is very difficult, which is why I always start off my Cal 2 class going, the better you are at differentiation, the better you're going to be in this class. But to be really good in Cal 2, you have to be like an ace when it comes to the differentiation. You've got to be, you can't struggle with product rule. You can't, it'll make it very difficult. Again, I don't make this up, okay? I'm only the messenger. This is what it is. Forward process Cal 1, backward process Cal 2. All right, I'm going to not go off on a tangent. I can keep on going and going. I'm not going to. All right, so I need to move on to something else. I hope you have the gist of what things are here with derivatives of exponential and log. So let's take a look at something. This is called logarithmic differentiation. Logarithmic differentiation. I want us to take a look at this. Let's say you have y equals x squared times the square root of x squared plus x over x cubed plus 1 to the 5th power. That looks like a big mess, doesn't it? And what if I now ask you to take the derivative? Find y prime. Well, if you're looking at it like this and you go off of what we've done so far, you have the quotient rule, right? So you have a top and a bottom. Now, when you do the derivative of the top, you actually have a product rule and chain rule. And it's a big mess. Now, it could be done, but this is the value of what's called logarithmic differentiation. So what we're going to do is we're going to try and use the properties of logarithms to make this easier, make it cleaner. You just have to follow. The first time through, it's kind of like, I got to show you, and then after that, you're like, oh, okay, yeah, I see that, or you don't. I'm going to come in on both sides of the equation and take natural log. Now, I'm choosing to use the natural log because I like the derivatives of natural logs. The derivatives of the natural logs never have that natural log A in them, right? Because that natural log A always turns into a 1. That's why we're using natural log and not some other log. Also, the fact that we had an equation means I can do this to both sides. You can always take natural log on both sides. You can always do E of both sides. It's kind of like you're always allowed to add something to both sides, subtract something, right? Multiply and divide type thing. Same thing here. You can always take natural log of both sides of any equation. Now, referring back to my notes real quick. Right there. Anytime you have a log, it doesn't matter what log it is, and you have division, you can always split that into 2 logs with subtraction, can't you? Right? So I have division here. I have natural log of a bunch of stuff divided by a bunch of stuff. So what I'm going to do is write natural log of y equals, I'm going to split it into 2 logs. Natural log of the top minus natural log of the bottom. Do you all agree with that? And then on this first log, I'm going to realize I have multiplication here, don't I? I have multiplication right between these two, right there. And because of that, I'm going to go back to this property again. This says that if I have multiplication inside of a single log, I can split it into 2 logs with addition between them. So this now becomes natural log y equals natural log of x squared plus natural log of the square root of x squared plus x. And then I still have natural log of, I'm just going to write x cubed plus 1 to the 5th here. I didn't really need that double parentheses here. As long as we all agree that that 5th power is on this. Any questions there? Sure. I'm out of room. Any guesses as to what I'm going to do now? What's that? That power, you like that power 5 here? You want to do something with that? What do you do with it? You can pull that out, right? There's that property. It says if you have something to a power. I said we'd use it today, right here. If you have x to a power, that x can be anything. It doesn't have to be just x. It can be any expression raised to a power. I can pull that power out. So that's what I'm doing here. I'm going to pull that 5 out. How about this 2 on the x squared? Yeah, I can pull that 2 out. And holy shit, look at this. Isn't all of this really raised to the 1/2? So can I pull 1/2 out of that? Okay, 2 natural log of x plus, you said the 1/2 comes out. What's still in that natural log then? X squared plus x. And then minus, you said the 5 came out, natural log of x cubed plus, x cubed plus 1. Now the left side of this equation, bring it along. Natural log y is still there, right? I want to make sure nobody makes a mistake at this point. Can you split that log up? This one with the x squared plus x, can you split that? No, the property says this has to be multiplication in here, right? Okay, so don't go doing that, splitting this into 2 logs and then saying, oh, I can pull that 2 out. You can't pull the 2 out. The 2 is only being applied to this x. Whatever power comes out has to be applied to everything in the log. That 5 applied to everything in here, so it could come out. The square root applied to everything in here, so it could come out. That 2 applied to the x, and so it could come out. So we are pretty much at a point that we have to, at this point, try and take a derivative. But we've cleaned this thing up significantly, right? We've made it 3 different expressions, haven't we? We can differentiate each one separately. Now, because we have natural log of y on the left side and not just y, I actually have to use implicit differentiation because I need to take the derivative of the left side also. Y'all ready? What is the derivative of natural log of something? 1 over that something, chain rule, times the derivative of what's in here. What's the derivative of what's in there? Y prime, dy dx, right? This is going to happen a lot, so just get used to this. The derivative of natural log of y is 1 over y prime. Questions on that? It's not dy dt, right? There's no rockets and stuff going around here, right? This is just, we're differentiating with respect to x. It's understood this whole time. Equals. All right. A 2 sitting in front of something comes along for the ride. What is the derivative of natural log x? 1 over x. Done, right? Plus 1/2. What is the derivative of natural log of u? This is our u. 1 over u times the derivative of what was in there, right? What's the derivative of what's in here? 2x plus 1. And then I'm done, right, with that part? That's the derivative of this. I have minus 5. What's the derivative of natural log of x cubed plus 1? 1 over x cubed plus 1 times 3x squared. That's it. Now you might be saying, you know what, I think I would have rather have done the quotient rule and the product rule, chain rule. I challenge you to do it that way. It is a mess. I'm going to clean this up. 1 over y prime equals, let's see, 2 over x plus 2x plus 1 over 2x squared plus 2x minus 15x squared over x cubed plus 1. All I did here, 2 times 1 over x, 2 goes on top. On the next one, I brought the 2x plus 1, put it on top of the x squared plus x, and then I distributed the 2 through the bottom. On this one, negative 5 and positive 3 is 15x squared, so negative 15 or minus 15x squared over the bottom. Everyone okay with this? We're almost there. The only problem we have, does anyone see it? 1 over y, right? I want y prime, don't I? So multiply both sides of the equation by what? Y, right? So I'm going to multiply the left side of the equation by y. Multiply this side of the equation also by y, right? Yeah? So I get y prime equals 2 over x plus 2x plus 1 over 2x squared plus 2x minus 15x squared over x cubed plus 1 all times y. But what's y? Wrong page. Oh, that's y. That's what y is, isn't it? So I'm just going to tack that on to the end. Now, you don't have to solve. You're done. Okay? So y was x squared plus or times the square root of x squared plus x all over x cubed plus 1 to the 5th power. we're done. That's called logarithmic differentiation. We're going to do more of that when we come back next week. So for homework, page 169. One through 27 odds. $41, $43. I'm not giving you any homework that has logarithmic differentiation on it. But if you are comfortable and you're ready to start logarithmic differentiation, then I will be assigning next time 51, 52, 53. To begin, those you could do tonight if you understood the logarithmic differentiation. Okay, those are all just log and exponent, just using chain rule and stuff. This requires logarithmic differentiation. The ones after this, there will be homework problems, but I haven't shown you how to do those yet. Have a great weekend. Was I? What? Oh, on the related rate problems? The related rate problems? Yeah, I just don't have them put together. Let me do this. I'll send an email out, and then once I send them out, I'll give you time for those. All right? It'll probably be problems that I'm going to send to you that you'll print out.